Hi everyone, welcome to this introduction to the Turbulence Fluid Dynamics tutorial set. Let's not beat about the bush, let's get straight into it. First of all, you're going to want to get hold of the plugin. Pop over to the DualSet site, there's the address up here. Have a quick read around, but you want to get on with it, so pop into Try. And you've got your two options here. Don't worry about the Lightwave and the After Effects. We're dealing just with the Cinema 4D. And you've got two options here, Apple or Windows. Download your demo version. Pop it into your plugins directory. And don't worry about my version is a beta version, but you'll have a TFD plugin folder. Pop in there, have a quick README, which will give you all the updates that have been going on. But more importantly, there's examples here, and all these lovely example files. They won't render off the bat, you'll have to simulate them. I'll discuss simulating later, but we've got plenty of things in here and we will be looking at these and breaking them down later on in the tutorials. Okay, so basically that's it. There's not much more to that. You just but do be aware that the examples are there tucked away. Okay, once you've done that, you'll find TFD in the plugin folder. Lots of goodies here we'll discuss later, but the first thing you want to look at is the help. It's quite a reasonable help. Not a lot of examples in here. They'll be coming in due time, but more importantly though, the explanations are very clear and concise. It doesn't beat about the bush, and if you want an answer to something, it's there without bothering too much. So it's a fairly good help system. The point being, the help system can only go so far. It gives you an explanation of what certain parameters do, but the best thing with Turbulence is to experiment and play. That's where you're going to learn, of course, from these tutorials, but experimenting and playing around yourself is the most important way to learn how to use the software. Okay, once you've installed it and you've had a quick look at the help, the first area you're going to be looking at is the preferences, which is in the standard preferences area. Pop down here and you'll see Turbulence Fluid Dynamics. TFD saves its data to disk and then reads that data back for rendering in what's called a cache, and you're going to need to set up your cache path here. Ideally on a separate very fast drive. An SSD will be good, but they're expensive and not that large. You will be dealing with many gigabytes of data, hundreds of gigabytes of data, and if you're doing professional long shots, you might even be looking at terabytes. So you want a fast disk. You don't want any programs running on it. You definitely don't want your operating system on it or your page file on it separate. A RAID would be nice, but I've just got mine on a single dedicated drive. And obviously you set that up as you would normally. I won't go into that. By default this is on, which is a very handy thing, so leave it on. It basically states that when you start a simulation, it automatically will save the project file, and it's called autosave.c4d, and it saves it to the same area that your cache is in. So if you do get a crash, and you will get crashes, it's not too much of a problem. You simply quit and then reopen the file from the cache, and it will be as it was when you hit the sim button. Okay, and you can go back and then make changes that you think may have caused the crash, or try it again. But it is very, very useful. It's a bit like the normal Cinema 4D project crash, but in some ways I find this one a lot more useful. Leave that on, automatic check for updates. There's no reason to switch that off. This section here is normally on. I'll discuss simulating obviously later, but what happens is every time you resim, you're going to overwrite your cache. It will pop up a warning window, which I find annoying, so I don't need it on. If you're a nervous person, leave it on. Otherwise switch it off. It's not really necessary once you know what you're doing. Okay, that's all there is to the preferences. Quite simple. Right, let's basically look at the let's just drag this out. Let's look at the container first of all. TFD works within a defined area called a container or a grid. Anything outside of the container is totally ignored by Turbulence Fluid Dynamics. You can resize this grid or container either here, which I don't advise you doing, and I'll discuss why, because notice how the voxel size is changing. The best way really is to resize via these settings here, okay? As I say, we don't want to resize there. You can if you want and then go back and rechange that, but you'll find if you've got a set voxel size, and I'll discuss that in a second, but if you have a voxel size you like, you don't really want to be changing it, so this is probably the best way to resize your container. Anything outside the container is ignored. Things inside are taken into consideration by the computational fluid dynamics. You can have an object half in, half out, and only the half that's in will be considered. Likewise, objects moving through the container, it can be animated, so I could have something that's emitting temperature out here, for example, and in this position it's not being taken into consideration, but as it moves through, it will start, part of it's in there, that will start being calculated. Fully in it's calculated, and out it's not calculated. So you can have things moving through the container. Okay. We don't need that cube, let's just delete that. Okay, now put that back to its default. What is the grid size and what are voxel sizes? Well, voxels are actually three-dimensional pixels, and the voxel is a unit that will contain all of the data that you're caching, that you're saving to disk, and that data could be temperature, density, fuel burn, etc. We'll get onto all these various channels later, but they're just very much like in a particle. You have a particle's mass, a particle's velocity, a particle's spin. Okay, these are channels of data that a particle can contain, and these are channels that a voxel can contain. And the smaller the voxel, very much like the smaller the pixel, the more detail you're going to get. And the easiest way to show you that is to, if we go into the viewport preview, we've got a section here that says show grid. And the grid basically is a two-dimensional representation of these 3D voxels. Imagine these as being tiny little cubes. And as we increase our voxel size, so we're going to get a lot less detail. I think it's quite obvious. I don't think that really needs too much more explaining. Just imagine that that's a picture. If the pixels were large, it would be very blocky. The smaller we get this, the more detail we get. Okay, very much like mesh resolution. But don't forget, these are three-dimensional. Now, the point of this being that if the temperature in this voxel is, say, 10, it's 10 everywhere in this cubic area, in this voxel area. Okay, so this is 10. If this one was 100, there's your sharp limits. There's 100 and there's 10. Okay, but as we get it smaller and smaller, now we could have a lot more detail in our temperature, because, well, even my screen won't show it. That's far too small. Let's try 0.1 mil to see that. Still pretty small, isn't it? Okay. We can see now that we can have 10 here, 100 there, 5 there, 10 there, all within such a small space. We're going to get a lot more detail, and we'll show you an example of that shortly. Let's just put it back to its default, which is a right click. Some of these you can right click to get back, and some things like this will not, but invariably you can go into here and reset to default. Okay, so voxel size is the level of detail. Let's leave it at a default of 1. If we have a look down here, this is some standard information you're going to get about the memory usage and the disk space usage that you're going to be needing. So let's say, for example, we want to work on this with a voxel size of 1. It's telling us we're going to be using 1.2 million voxels. If we were to fill the whole container, we'll be using 1.2 million voxels, made up of 105 by 105. Don't ask me what those numbers mean, because they don't relate to those. Well, they do relate to them, but as we increase the size of this x coordinate, we'll see that this is going up. Why it's 105 is something to do with the maths that I don't fully understand. That's just generally, it's handy to know how many million voxels you've got. It gives you a rough idea of how much detail. But this is the most important thing. This is going to tell you approximately how much CPU, how much RAM you're going to be using if you were using the CPU to simulate. Now you can use the CPU or the GPU to simulate, and the GPU typically will require less memory than the CPU. So this is telling me at the moment, if I was to fill the whole of this container with smoke at 1 centimeters, I'm going to need 79 meg of RAM for if I was going to render on the CPU, and I'd need 44 meg of RAM well, yes, it is RAM from the GPU. We'll talk about upresing later. This is telling me that my cache per frame will be 4.9 megabytes on disk, okay? Not in memory, but on disk. Well, actually, that could be memory, because I don't think it will be that large on disk. We'll have a look at that in the help. They're just handy bits of information, but these are the two critical ones. How much memory have you got? Now, I've got 64 meg of RAM. Let's say I had 12 meg of RAM. I can look at this and go, right, I've got 12 gig of RAM. How much detail can I play with? Well, I can bring it down, and I can go to about there. I'm on 10. If I were to go much smaller, now I'm going to get to a point where I'm going to run out of RAM. But, and this is a big but, this is if we're using the whole of the container. That's how much memory you'd need. But very rarely would you use the whole container. You would be using generally only a small portion of the container. Even for quite a large explosion, you'd only be using at most 3/4 of the container. So don't take that as gospel. And it will come up with a warning if you try to simulate and you haven't got that much RAM. It will say, should the container be full, you're going to run out of RAM. Don't worry straight away, because it's very rare you're going to fill a whole container. But do bear in mind that this is there to give you some advice. It will also give you an idea of how fast it's going to be. It's going to take a lot longer to simulate the more complex simulation with a smaller voxel size. So let's just set that back to default, and we'll have a look at this section here, simulation caches. As we checked in the preferences, we set up a default cache path. If we hit new here, it will pop up using the default, which was my FTFD, and now it will give me TurbulenceFD caches. Now it's saying 012 because I've got plenty of caches I've done before. Yours will probably say 01 or 001, and it will create a cache, a series of caches here. We can create many of them. Okay, so we can do different experimenting with different parameters and use them all, cache them to different caches. And then we can go backwards and forwards between the two of them. And we could actually have several containers, one of them using this cache and the other container using that cache, okay? I'll discuss that base path later. We don't need to worry about it at the moment. We can delete these caches. We don't need them. And in fact, you really don't need to set up one straight away, because by default, once you start the simulation, it will automatically set up a cache. And what do I mean by caches? Let's have a quick look. Now, this is my cache path. This is the one we just created, nothing in it. Here's one I worked on earlier in good Blue Peter fashion. it's got a few things we'll discuss later, but most importantly, it's got this autosave, which I told you, that automatically saves the project as soon as I hit simulate, and then it creates all these cache files. Now these ones are coming in at 150 linear meg, and they rise up to, or rise down, sorry, these are the first ones, aren't they? 0 down here. So it's going from 1000 kilobytes up to a meg. I might even have some more that are bigger than that. I often empty them out as soon as I finish. When I've emptied a cache, it does tend to keep the actual folder. Here we've got caches. These aren't too big, but they can get very, very large. Okay. So there you go. That's where your caches are saved, and that's what they look like. We've got a section here to lock your cache, which means once I've done that one, I can lock it. It's like a protection tag. It means by mistake I can't overwrite it or mess around with it. Compressing cache basically make your cache files smaller. So if you're doing any network rendering, that can be handy, or if you're worried about disk space size, it will slow things down a bit because obviously there's overhead in compressing. I very rarely use it. Down here are the different channels that we can cache. As I said, as with particles, you've got spin, mass, what have you. In our case, we'll be dealing with temperature, density, fuel, burn, velocity. Caching collision is a specific troubleshooting thing. We won't look into that at the moment. We might look into it a lot later. By default, you're caching temperature as your data. And then this section here just gives you some basic information about a frame. At the moment, we haven't got anything cached, so there's no data to show here. But we'll look at that as we do a sim, which I shall do now. Okay, let's do a quick let's get started sim. Quite straightforward. First thing we're going to need is an emitter. An emitter can be particles, objects, what have you, but to start off with, it's generally suggested you use something like a sphere, okay? And we'll leave it exactly where it is. We don't need to mess around with that just yet. Now, to make an emitter, we need to give it an emitter tag, which is simply a right-click, TurbulenceFD, and an emitter tag. Quite straightforward. Various sections in here. We won't go into just yet because I'll have a whole section on emitters later. But for our intents and purposes, we know by default we are caching temperature, but we're not actually emitting anything. So let's emit some temperature by just giving it a 1. That's all we need to do. And if we now go into the container, if we look into the simulation tab, we'll see we've got those same channel settings here: temperature, density, fuel and burn. Burn is not active, neither is fuel, neither is density, but by default temperature is active. Okay, so we're actually emitting temperature from our emitter. We're actually simulating temperature because it's active, and we're caching temperature to disk. Okay, so those are the three things we're going to need. The next thing we want to be looking at is rendering. Let's do a sim first, and then we can consider rendering. So we've got a cache set up. It's a simple case of just hitting start cache simulation, okay? Or basically I've got this window here, which is a simulation window, which pops up. And it gives you the options of what sort of simulation you want to do. We can do a cache, interactive upres, but by default, just for starters, we just want to cache data to disk. And we've got a choice here of what we want to use to be using to doing the simulation. The GPU is a hell of a lot faster, simply because the bandwidth of the memory of the GPU is so much faster than the CPU. I'll run it on both. On this simple test, you probably won't see a great difference, but on more intensive simulations, you'll see a massive difference. So by default, you should normally pick up your GPU as the first renderer. I was using my CPU earlier, that's why it sticks with what you used last time. we've got options to render and finish and update timeline editor. We'll have that on, okay, that's normally on by default so we can see what's going on. I'm going to switch this grid off because we don't really need to see that at the moment. And we just basically hit start. And there you go. And it simulated that in 4 seconds. Let's just put it onto the CPU and see what the difference is. Very little difference because it is a very simple sim. Now, so what have we got here? What was happening? Well, we were emitting temperature. The simulation was simulating temperature. And we have a concept of buoyancy. Hot things rise, and that's what buoyancy is. So what was happening was the temperature was rising. If we look at our viewport preview section, we can see which channels we can see for the viewport. And we're using temperature. If we tried any of the others, we'll get nothing because we didn't have them active. Okay, the only thing we had active and caching was temperature. I'll discuss the shader later, but at the moment something to consider here is this little green box in here. Now, noticed earlier I said that it said we were going to use 44 megabytes of memory on the GPU and 79 megabytes of memory on the CPU if we were rendering with either of those. Unfortunately, it doesn't keep the data here live, but when we actually do the sim, you'll see the data being shown. It would be nice if it kept it there for consideration purposes. But let's just pop this voxel size down a bit, because it'll simply slow things and we'll be able to see a lot better. Now it's saying I'm going to need 2.4 gig on the GPU and 4 gig on the CPU. Now that, don't forget, I'm using the GPU for the screen monitor, so there is overheads. Okay, so this figure will not really exactly match that, but it gives me a rough idea. I've got 6 gig of RAM on the GPU. If I go up to about 5.5, it's going to start throwing a wobbler. 5.8, 5.9, it should automatically switch over to the CPU when it runs out of GPU memory, but there's a problem with Navier, and it doesn't always do it. Well, sometimes it does, but doesn't always do it automatically. And you can manually switch over, but you really have to keep a close eye on it. Let's just run it now with the GPU and we'll see. As I said, it was saying I would need 2.4 gigabytes. What's it say it's using? And it's not even yet up on a gigabyte, simply because we're not using the whole container. Now I'll just stop that here, and that's gone again, unfortunately. But the reason why we're not using the full amount, and the reason why we're not using the full container, is we have a thing that is called an adaptive container. And that's a setting that's on by default in the solver, and it's ticked here, adaptive container. What it is saying is that the computations will be constricted to only the areas that TFD deems important, or we deem important. There is temperature going on here, but it's so slight and so low, it doesn't really interest us. We're not going to be using it for rendering. Why bother calculating it? And there are settings that are actually hardwired into the program, but there are also settings that we can adjust, and they're called the clip settings, clip below. So this concept of clip below 0.001, anything below that is going to be totally ignored. Okay, and the temperature of the rest of the box or the container is so low that it's going below this clip value. It's being ignored. So what we've got is we're saying this is the area that we're concentrating on. We only need to calculate this area, so why waste time calculating the rest of this area? Now if we would switch off the adaptive container, we did 165 frames in 12 seconds. If we switch it off, now we notice that A, it'll be a lot slower, and B, it's going to use a lot more memory, because that green box now has gone automatically to the full size of the container. We're using a lot more RAM than it suggested for the card simply because we've got overhead. I'm running a video recording. I'm also using this monitor. Ideally you would have two GPUs, one your less powerful one just for running your screen and keep your powerful Titan purely for the sim data. So there you go, it's a lot slower. The green box is telling you the area that's being calculated. You don't really want to switch it off. I can't think of an occasion when I've needed it, the whole container. If you're doing something very, very complex and there's a lot of fast movement, maybe then, but 99.99 times out of 100, keep that on and look at the speed difference you get. And it's adaptive, it grows and it shrinks and it grows and it shrinks. Okay, so we've simulated, but it's no good if we can't render. We know that's gone to disk and it's cached here, and that's the size of the total size of the cache. We know we've got temperature. Let's now have a look at rendering. By default, the only thing that's on is fire. Smoke is off, okay? And fire by default is set to map to temperature. So we're good to go really. If I now hit render, there we go, we've got some fire. Now, we could map fire to anything else, but we haven't actually saved any other data, fuel burn or temperature, so we'll get nothing. But if we put it onto none, we can actually render smoke. But the only data we've got is temperature, so we'll just fire it up with temperature. And there you go, we've got some smoke. And we could even give smoke let's give this some shadows. Now, to be honest with you, shadow maps, soft or hard, it really doesn't make a difference because of the way TFD computes shadows. The difference will be if this is casting shadows on the floor, you'll get a speed difference. But I generally tend to just go with ray trace shadows. Okay, so simply from using temperature, we've been able to shade smoke, and we can shade the fire at the same time. Okay, so there you go, very simple. Just for the fun of it, let's add in a few other things. We've got concept of turbulence, which is the name of the game, so we can add some turbulence to that. 150, and we'll sim that again. And we can actually, let's increase the larger size of that turbulence, make it a bit more wavy, and we can render that out. Now another concept we have, instead of caching, we can actually do what's called an interactive sim. Now this is not going to cache any data to this, so anything we do here we can't reuse, but it is useful for testing purposes because by its definition interactive, it means we can make live changes in the simulation window which will update live here. Now I might get a crash, I might not, because of the fact I'm doing a GPU sim and I'm recording at the same time. So let's see. Let's get our fingers crossed. Notice the timeline might move, and we're not caching any data. So let's put the turb intensity down to 0. In fact, let's stop it and put the voxel size back up so we get a lot faster feedback. Okay. Now don't worry about my the flashing screen. That's, I think, an issue with my video card when I'm recording. If we can increase that, and we can increase that. Okay, we can set that at 0 again. Let's play around with the wind. Let's make the wind 100 in the X. So I think you get the picture. interactive. It doesn't save anything to disk, but it allows you to do some experimenting live. If you wanted to tweak things, basically. I don't often use it, but it's there if you want to use it. The other concept we have is a thing called upresing. Let's put that turbo intensity back to, say, 100. Let's give that a quick sim and bring this wind down to 0. Okay, so, and we won't render the fire, we'll just render the smoke. Oh, sorry, we can't render anything because we're on interactive. We won't cache any data, so we need to put that onto cache. Okay, now if we render that out, we get fairly interesting, but it's not a lot of detail. And if we look at our container, we can see that a full container would have used 1.2 million voxels. And would have used this much RAM, okay? But bear in mind that it's 1.2 million voxels. Now, we could re-simulate this, and this time lower our data. Let's say it down to 0.25. Lowering the voxel size. Takes quite a while to sim. And we get much finer detail. But by definition, when you actually increase the detail, you change the overall nature of the simulation. And I will be discussing this later, but it's something to bear in mind that if you were to do a sim at a certain voxel resolution, such as there, and you like the shape, but you want more detail, if you were to lower the voxel size, you will lose that shape because there's a lot more going on within the voxels. You wouldn't keep this overall shape. One way to keep the overall shape is to what is called an upres. To do an upres, you need the cache velocity. We will be discussing upresing later, but let's just sort of give you a quick demonstration. You would need the cache velocity. Remember, we're on 48 at the moment, okay? So I need to resim because I need to recache the velocity, or cache because I didn't cache it before. Okay, and let's go to 48. Have a quick look at what we've got there. Now, if I simply change from cache to upres, I have to bear in mind that you cannot use the GPU for upresing, but so I'll put it onto the CPU. It shouldn't automatically switch to the CPU. What is upresing? Well, what it's basically doing, it's subdividing again. It's halving. By default, it's on an upres scale of 2, which is saying I'm halving the voxel size. So I'm going from 1 to 0.5. So it's recalculating from the old sim data. But it's not changing the overall shape, the overall size. It's adding sub-grid detail, as it were. I think in Mac's fume effects, that's called wavelet turbulence. Okay, so it's adding detail into the data that we've already got. And if we just do the upres on that, and it we got a crash. Okay, we'll try it again. I don't know why it crashed and done it. It could well be because I'm recording at the same time. I'm going to switch this update timeline off so we don't get an automatic update. Fingers crossed we don't get another crash. And it has again. Okay, sorted out that crash. Right, I've done an upres. Now, notice that when I did my initial cache, I cached with velocity, and once I've got that velocity data baked in, as it were, into the cache, I then did an upres. Now I don't need the cache velocity again, hence I get a much smaller cache size, even though I've got twice the amount of detail. And the reason being that caching velocity is very expensive in terms of disk space, and it will also slow down your simulation times because of that. Now let's just have a quick look at the difference. What we can do is take this container and duplicate it and move it over here. Now I haven't moved the emitter. The emitter is still in place, but the data moves with the container. Now if we actually let these run, we've got two identical simulations, okay, and it would probably be better if we got this light smack dab in the middle. Let's just create a camera so we can see where we are, and let's move this light so it's roughly here and make it infinite. Okay, so it should I'm going to move that over, get the light over. Whoops, we just wanted to move the light, didn't we? Now I have to move the two of them. I'm just fiddling, but I want to get it so that they're pretty much lit the same, and we should get two identical, virtually identical. They are identical, the data is exactly the same. Now if on this one, which is the one on the right, I now tell it to use this cache, okay, it's using the Upres cache, we can directly compare the difference, okay, a lot more detail, but exactly the same shape. If I were now to, let's take a third container, and let's move that one in, whoops, let's move it in the middle here, pull out a bit, let's separate these a bit. Let's put the emitter directly under there so we know it's still there. Okay, so this one here, we've got showing the upres. We're going to have this one here showing the default. And what I'll do is I'll resim this one, but I'll do it at 0.5, which is half the voxel size, twice the detail, which will be equivalent to this upres, which is twice the detail. And we'll make sure that we don't need cache velocity because I won't be upresing this one, but I have to make sure that I'm not on upres here. I'm on cache, and I want a new cache so I don't overwrite those ones, and I'll put it on the GPU. Hope this doesn't crash again. Let's fingers crossed. Just run that one. Okay, these are being picked up because they're being read from data because it's updating the timeline editor. Now, it's just, okay, that swears off. So this one is twice the resolution as this one, and this one is the upres. And let's see what we get here. Now these two will be identical in shape, but there's more detail being added into this one. This one has got the detail automatically calculated in it because it had a much higher resolution, a lower voxel size, but the overall shape changes, okay? Because as I say, the more detail you've got, the more voxels can interfere with each other, can mix things up, temperature moves and flows around. You get a different overall shape and overall change. So that's something to bear in mind. If you've done a simulation of this size, perhaps even better if we can get to an area where it's a bit more wavy, say here. If you do a sim at this res and you say, oh, I like the shape of it but I want more detail, well, if you were then to up the detail, you would probably, you'd see more if this had more turbulence in it, but you're losing the overall shape you're not getting exactly the same shape. Whereas here, by using an upres, you're getting exactly the same shape, you're just adding in more detail. Okay, so say you like this curl here. Well, we've kept it here, we've just added more detail. Whereas here we've got a, not a completely, but we've got a different sim, we haven't got that curl there, although we've got high detail. So it's up to you how you want to get more detail in. The other thing is that when you use higher or lower voxel sizes, which is high resolution, you get a much tighter and smaller sim. Not so obvious here because we haven't got that much going on, but if it was an explosion you would notice it. And you can actually see it here, but the green container is smaller here than in these two. Okay, this stays the same, although it's got more detail, it's an up-res. The overall size is identical. Okay, but this one tightens in, and the smaller your voxel size, the more detail you've got, the tighter your sim will be. Okay, so that's a quick sort of overview of what we're going to be looking at. There's a lot to cover in these tutorials. Play around, you know, mess around on your own before you go on to the next one with this temperature and turbulence and what have you. Get your emitter moving around, get a feel for it. Feel free to start adding in other things. You can add in density if you want. By default, if for example, let's kill these. We'll keep this one. We'll keep the middle one. We'll kill that one. We'll move this over so it's emitting into here. It doesn't have to be below that, by the way. I'm just putting it there so in case I move it. So I'm getting confused myself now. That's my container, right? Definitely. Okay, that's the container I'm dealing with. Yes, we could emit density of 1, and we can go into our viewport and tell it to view density. But if we were now to kill the temperature and we were to sim that, nothing's happening. And what are we picking up? Smoke show. The smoke shows on temperature. There was temperature in there. It's picking up temperature from somewhere, but it shouldn't do it. Let's clear all these. Delete that, and delete that. Okay, so we're not giving it. Oh, we had temperature. Let's kill the temperature. Sorry, and just emit density. Now that green box shouldn't really move, because what's happening is although we're emitting density, and we can render our smoke with density, we're not actually emitting any temperature, so the density is just sitting there, it's not moving. Well, we didn't get anything actually because we didn't have density on. Density has to be active, so if you're going to play with it, activate density, and it comes up as automatically cached when you activate it. Let's try that sim again now. Okay, now we've got some density. It's moving around simply because of the turbulence. If we were now to switch this turbulence off and sim again, it doesn't move, it just sits there. Once we add the temperature back up, we get our density to rise, and we can go now into the turbulence. Okay, and again we could shade either with density or with temperature, because those are now the two channels that we cache, and it will tell us what's available. It's telling us we've got available density and temperature, so we can mix and match. We could do fire with temperature, and smoke with density. Okay, well there you go. Play around with the settings, and we'll move on to the actual plug-in proper. We'll start getting into some of the detailed settings. But this was basically just an introduction, giving you some ideas of the concepts behind the plugin, getting you up and running with your first simulation, so you can sort of go off and start playing with it. Obviously you're going to want to know a bit more. We've got many hours of stuff to come to look forward to as we start digging into the nitty-gritty of it. Okay, thanks. I'll see you in the next tutorial.